Every textbook will tell you the universe started with the Big Bang.
But if you take Einstein's general relativity and run the tape backward, you hit a massive wall. The initial singularity.
At time t equals 0, the math breaks down. You get infinite density, infinite temperature,
and infinite space-time curvature. In 2001, physicists G. Sudhakaran and C. Sivaram proposed a fascinating fix. What if matter doesn't just pull space-time down under gravity? What if, at extreme heat, space-time actually pushes back? Let's break down how thermal space-time repulsion actually works.
Whenever extreme matter appears in flat spacetime, spacetime responds in two ways.
First, it curves, creating standard attractive gravity. Second, it reacts to temperature and entropy to create a repulsive interaction. Think of it like an elastic sheet. Heavy objects make it dip downward.
But if that object gets unimaginably hot, the sheet springs outward against the pressure. They modified Einstein's field equations by adding a new repulsive tensor, S or Ij.
This new term is driven directly by temperature and entropy density.
Where does this repulsive force physically come from? Quantum field effects and in supergravity theories, extreme heat might release massive spin-one particles called graviphotons, exotic bosons that mediate a powerful anti-gravitational repulsive force. So what happens at t equal to 0, the moment the Big Bang usually breaks physics? In this model, temperature hits a maximum limit, 1.1 times 10 to the 32nd Kelvin. At this threshold, repulsion completely cancels out attractive gravitational density. Effective density goes straight to 0. No infinite singularity. No broken math. Even cooler? Time doesn't start at 0. For negative time, the universe was contracting. Without complex inflation models, this simple thermal tweak solves major cosmological headaches.
The flatness problem? Fixed. Early spatial curvature naturally calculates to 0.
Cosmological acceleration? Explained by a hyperbolic space geometry, k-1, driving an expansion that perfectly matches observations of distant supernovae.
Smooth transition. As the universe cools, Sij vanishes,
leaving us with standard, battle-tested, general relativity. While this model introduces an extra term, it proves the Big Bang singularity isn't inevitable. Space-time may have thermal properties we are only beginning to understand. What do you think? True infinity? Or are we living in the aftermath of a cosmic bounce?